Welcome everyone to the webinar for today, Unlocking the Power of Generative Design. Let's get started here. So first thing I'm going to talk about is, everyone's on mute, like we said, listen only mode, except for myself. And then if you have any questions, like Ashley said, make sure you just type those in and I'll try to cover those and read those at the end and get to that because we have a lot to cover here. So first, what is Fusion 360? So we're talking about Fusion. They've rebranded just called Fusion. Well, it's a cloud-enabled platform. So with this, we've got our different information about product definition. So we can design things directly in Fusion. We can do our engineering on it. We can also do our production engineering. So we can do our simulations. We can do our manufacturing, our tool sets we can add in there. We can add the manufacturing, the CAD CAM directly into the product as well, and then send that down to the shop floor for our production for the machinists or the machine operator. So all the way from design to the manufacturing, Fusion will cover. And today, really, what we're going to be talking about is like the engineering / production engineering area. So these two topics in the middle here is where we're going to be covering with generative design. So really, what is generative design? If you're not familiar with it, it uses the biometric algorithms derived from nature to create design iterations. So Autodesk had taken algorithms directly from nature, so they've reverse engineered algorithms from nature, and it's used to create those designs directly for you in software and using artificial intelligence and the actual software for that, cloud computing. So when we think about generative design out in nature right now, currently, we're thinking about, hey, this is a dragonfly wing. If you think about the structure of a dragonfly wing, what does it look like deep down? How is it built? Also, our bone structure, how is that really defined and built by nature? It really is, it creates and constructs the design for structure depending on where it's actually needed. What is it used for? What does it need to be made out of? Where does it need to be structurally held and strengthened at? So that's where it's using those algorithms to create that. It's really the artificial intelligence that's doing this. It's actually a design exploration through creating designs. So we have multiple outcomes for exploring those designs. So we're giving it we're giving it some objectives, just like how nature has an objective to build something. We're giving the software objectives to build something, and it's coming out with the outcomes, the solutions for us. So we're exploring all those designs that come out, whether we need, and it's going to give us all those outcomes. And depending on whether we need to maximize the strength or create it out of a certain material, we can explore those different outcomes. And that technology is now available in Fusion. It's been available for you for multiple years now. So with our traditional development processes, we've got a design that we usually have someone manually creating a bunch of different concepts. Okay. With those different concepts, we take a look at those and we explore those and say, okay, is it good for manufacturability? We evaluate those for costs. We evaluate those for strength or the material, whether it can even be done. And then we pick and choose one product or one outcome and then produce that. And usually we come up with just a design that's pretty, it's more like what I would call this like legacy designs, like what a human would think about our shapes, our blocks or thicknesses, what we think that we could design. But with generative design, what we're doing is we're taking this, throwing our objectives inside of the software, and it's coming out with a lot of different outcomes in this, and it's optimizing each outcome that it produces depending on the material that we give it, the manufacturing process we give it. And then we can actually pick and choose instead of doing this all manually and thinking about it with our human limitations. we can actually use the software to do this, and it will spit out the optimized version of this, and then we can pick and choose which one we want to produce. So really, we have problems, of course, with design. So the problem exists, and we can input our criteria with for the design. And then with the software, we can explore all those possible solutions. When we think about the manufacturing methods that we are used to and we can actually solve for in generative design, well, we've got additive manufacturing, die casting, 3 and 5 axis milling, 2.5 axis milling, and 2 axis cutting. We can actually optimize those for each different outcome inside of generative design. And here's a quick video on what they've done with that bracket that I've shown the previous slide for the motorcycle here. I'm just going to play this quick, and I'll talk through it as we go. So we've got an existing design that we've done with the human has created. And what we're doing here is that we are picking points, picking objects out of that human design. We create some new solids, some new components out of this. I shouldn't say new components, but the areas where we are actually attaching to the verticals or things that need to be bolted onto each other. We actually pick those, and then we're going to pull those out of the existing design. So really, we could start with this shape, or we could take a legacy design and pull that information out. Or we could just, like I said, start with something like this, and then we can send that through generative design. So this is a nice little process here we're doing. So we're picking those, and we're saying that this is preserved geometry. Preserved geometry means that this is areas that need to be kept. This is geometry that needs to be kept for generative design to work off of. So of course, yeah, we need cylinder shapes to be able to hold on to tubes. We need things that for bolting connections. We need holes in there. So we need to keep those, and we define those by using that preserved geometry. Then we set some loads on that. So it's right now it's setting some conditions on there, some loads and constraints on there. So that's what they're doing here in the video. And then they're setting some objectives to this. So they set safety factors, displacements, things like that inside of this for the criteria of what we want to do. And then also the manufacturing methods, whether you want it to do it with additive or milling, what type of milling inside of here. 2-axis cutting they added too. And then what we do is we can generate that study and come back with outcomes that the software and AI has created back for us that maximizes it and optimizes it depending on the manufacturing methods and the materials that we actually add inside of the software. I'll play this a little bit more. And then after that, once we pick one that we would like, an outcome we would like, we can actually look and see where the stresses are. We can actually export this out and we can modify the design if we think it needs to be a little bit optimized. We can also then export this out and then export it out to like a manufacturing workspace and then actually manufacture that with our CAM tools inside of Fusion directly. Okay. So that same bracket that they've shown there on the motorcycle. So with the human design, right there in the center, bottom center, we're looking at a weight of 3 kilograms with a safety factor of 2.7, but the cost is about $160. Throwing it through generative design with different studies and different materials and different manufacturing methods. On the left-hand side, we get the 3-axis milling there. And it's a weight of 2.3 kilograms, which is a less weight. So that's a savings of about 23% on weight. A little bit lower safety factor, but it might still fit within the criteria. And our cost is lower as well. We also have the 2.5 axis generative, which is in the middle of the top. Also 23% savings. Safety factor is quite a little bit lower there at 2.2, and then our cost is actually $130 only. And then on the right hand side we've got additive, and additive of course is going to cost a lot more, but our weight goes down a lot more too, because we're actually constructing the product we're printing it out instead of pulling material away. We're actually printing it out exactly how the design should be, and it optimizes for additive right at that point too. So some of the problems that generative design solves, and some examples of this is with Hyundai Motors. They've done a mobility vehicle, and they've created some of the structure for the vehicle here with generative design. So some of the frame structure and some of the structure for like the wheel, like around the wheels here, and the components inside of there. So for new product design, so you can use that for that. So also for part consolidation. So General Motors actually taken on the left-hand side here. There's a screenshot of an assembly that had 8 different components in it. And what they've done is they've taken the preserved geometry of the areas where it's being bolted or where it needs to connect, taken that, and then they've used generative design to make it one component instead. And what that will do is it will not only cut down on tolerances because you're not putting pieces together, so it's just one component now, but they've made it 40% lighter and also 20% stronger with just one component instead of the 8. And then also with Honda there, they've actually redesigned a crankshaft with generative design where this has output a design that's 50% weight reduction on this using the additive manufacturing method. So thinking of something like race cars, or even for something like aerospace, when weight really matters, that's where generative design would also come into play. So we're thinking about industry segments, talking about that. The aerospace industry uses it, automotive, your weight savings, your strength per weight. Also for medical segment, and also your industrial machinery, consumer products, dental, oil and gas, and architecture and construction. So architecture and construction, there is a form of generative design within Revit as well, for placing different components, or not components, but parts within a building, or optimizing walls, or where they should be depending on generative design, and optimizing that there. So you might have heard some topics called topology optimization. Really, that in simplification, in simple terms, that's like removing geometry. So you start with a shape and you're removing the geometry out. But with generative design, we're actually giving it some constraints and some objectives, and we're telling it to create the geometry in there. So generative design. So when we go to create a generative design study, this is directly in Fusion. And with Autodesk products, I like to say, okay, let's start from left to right. So we've got some different buttons and tools inside of generative, and we're going to edit the model, design, use the design space to add our preserve and obstacle geometry. We have some design conditions where we're adding loads and constraints in there. We have our criteria, whether we want to maximize the strength or the stiffness in there, and also, or we want to minimize mass. We also have materials that we can add to it, and then we can also then generate it at the very end. So left all the way to right is kind of the workflow for this. And when we're thinking about generative design, I like to mention this too. So we can set up the study and run, previewer and everything, and do that. But if we were going to go and generate some outcomes out of this in the commercial side of things, yeah, it's going to take some tokens because it's using processing power on the Autodesk side. So it does use some tokens for this, and tokens usually are around $1 per token. And if you're interested in more about that, you can reach out to us. But yeah, for generating the outcomes, it does use those, and we can explore those results after it's been generated. And then if we want to create some designs and pull one of those outcomes out and actually use it inside of one of our assemblies or design, it does take a couple tokens to then generate that file out for that outcome. So when we're thinking about generative design, once we start doing this, there is some information that we have to remember for for generative design. And I'm going to show an actual demo of creating an easy bracket for this on this webinar here. So first thing we have to remember is there's no magic solution button. So we want to focus on what we have control over, our preserves, our obstacles, the geometry that's there, and the things that the geometry that we want it to grow around or create around, and things that might attach to it. Also, we want to control the loads and constraints. So if we're throwing a huge amount of loads on there, or multiple constraints where they're not needed, or if we're adding too many constraints, then it's going to probably fail and probably not be what you want in the outcome. Also, with our manufacturing methods, we don't want to throw every manufacturing method on there. What I would recommend is we would do multiple studies on this on a design in generative design. So we'd have a manufacturing method probably per study, but we can do a couple manufacturing methods per study if we wanted to. We just got to remember though that it's trying to optimize all of these things as it goes. So it might take a little bit longer. We might get less outcomes depending on what we're adding in here, and also the materials. So just think about what materials you want. So if you are designing and it's going to be steel, let's actually make the material out of steel. Let's not try some weird material unless you really want to do some conceptual design and actually think about, hey, let's maybe think about, let's make this out of a nylon, or let's make this out of something else that may be possible that we could use in our manufacturing method, and then maybe consider that and conceptualize that, and we'll see. So, but really, like I said, with the no magic solution button, be methodical about your studies, show intent in every step that you're doing. And there's also going to be the trial and error. So you might come out with an outcome and it might not be exactly what you want. So you might have to go back and add some more preserves or obstacles in there. And you might have to add and create multiple studies. So I'm going to show a quick demo of the caster wheel frame. So you can see here at the left-hand side, we've got the legacy design. Somewhat we see the caster frames for things that are purchased out there right now. But what we're gonna do is we're gonna send this through generative design and optimize that shape depending on the loads and constraints and the objectives that we give it. And hopefully we can come back with something that's optimized and show you how this works. All right, so first thing I'm gonna do, I'm gonna pop over to my Fusion, and we're gonna start with that caster wheel here. So as we're designing things, we can design things with our legacy methods if we wanted to, or we can just say, okay, let's just design what we actually need. But right now I have this legacy design that has a caster frame in here that looks like this here. First thing we do is actually we can switch over from design to generative design in here. And what we do when we switch over to generative design, it's going to ask us to create a new study. So we're going to use this structural component study. There is fluid path studies inside of Fusion for actually generating the correct, optimized path of fluids as well. But with the generative design webinar we're doing today, we're going to do the structural component. So we just create the study. And at this point, it switches over to our generative design workspace. And with this, we've got we've got our design in here. But what we can do is we can turn on or off our components that we don't need necessarily. So for example, like I'm not going to need this wheel right now. I'm not going to need to see that. I just want to really keep on this frame component at this point. I'm going to turn off this ball bearing. Let's turn off that top plate and also this threaded axle with the bolts at the end. So we end up with something like this. And this is what we can use to start out with our generative design study. What I'm going to do is I'm going to show how to create our preserves and our obstacles for this to start our generative design. So I'm going to switch over to my next one here. It's just the next step out of the way. So I'm going to start my preserves and obstacles. And it's pretty easy inside of generative design. and how to do this. So what I'm going to do here is I'm going to come up to my edit model button. So we already had our study created. That when we switched over the generative design workspace, it already created a study for us. You can see it's called study 1. And what I can do here is I can edit the model. And when I do the edit the model, I can come in here and now I can create my new solids if I wanted to. I can create some connector obstacles. And when I do this, it's actually going to just create geometry within the generative design workspace. It's not actually editing my design, but it's just creating new solids for me to use for that preserve and for those obstacles. So what I would do is I would come in here and I would say, okay, let's make a obstacle, because we don't want, when we go to create, or when we go to produce this generative design outcome, we don't want it to grow into this area inside here, because that's where the wheel is going to be placed inside there. So what we're going to do is we're going to create an obstacle geometry. So what I do is I come in here, I'm going to create a new sketch, and I'll place on that face. And I just go ahead and create my center diameter circle. And we'll say it's 7.25. We'll just do that for my wheel. Finish my sketch, and let's extrude that out to the next side over here. Oh, and not join. Cancel that, sorry. Let's do this, extrude that, and extrude that over to here. And we're going to make that a new body. Okay. So that would be an obstacle for keeping generative design from growing. So when we're thinking about this, I like to think about this as something in nature, like ivy or maybe a bonsai tree. We create some obstacles for it to grow around. So it's going to start, and we're going to create preserve geometry around this area in here where it's going to bolt to that axle in there. Also some preserved geometry up here at the top where it bolts to the top plate there. And what it does is it says with this obstacle geometry, from this area here where it's bolting, do not grow inside of that obstacle. So go around that obstacle there. All right. So when I hit finish edit model, I can say, okay, that's my obstacle. Okay. And you can see now it has turned red. So that's going to be an obstacle for this to not grow into. I can also, in my edit model, add something called connector obstacles. This is something great for like bolting locations. So with like bolting holes and everything like that, I can pick a first part of my shaft, second part of the shaft, and then say, hey, let's have a bolt head on it. Or if it needs some tool clearance, we can add tool clearance on that as well. Okay, so with this, I can define whether we want some obstacle in there for the bolt to be able to fit, or the tool clearance to be able to fit a tool inside there so it doesn't grow into there, so we can fit that tool in. I can do it for that side. I can also do it for the other side. Okay, when I hit finish edit model there, you can see that since we're using a connector obstacle, it automatically takes that and sends that to the obstacle geometry. Then also what we can do is come in here, and I'm going to create a new sketch on this, and I'm going to create a diameter circle here. I'm just going to use the same diameter of that down at the bottom. Finish that sketch, and then extrude that out to here. And I'll say that's a new body. Okay, and that's going to be my preserve geometry then at that point. So I'm going to finish edit model, and I'm going to say, okay, preserve geometry is that location there, because we need something to have that axle go through the bolt to down there for the inside of the wheel. So if I turn off my model components now of that frame, you can see now it's starting to build some areas here. So we got some preserve, we got some obstacles. So essentially what this is going to do is it's going to start at this preserve, and I'm going to have some other preserves here at the top for bolts to that plate. And it's going to take that and grow that from this preserve geometry up to that other preserve geometry by going around the obstacles. Okay. All right. So we talked about the preserves and obstacles. So with those also, yeah, we're editing the model. With the preserves and obstacles also, preserves must see each other. So I did those that preserve on the left-hand side of the bolting location down there at the wheel. Once I have the top preserves here for that plate at the top, what we need to have is a line of sight from the bottom preserve up to the top preserve. So we can't have a flat plate that we set a obstacle on there so they can't see each other. So it's a direct line of sight to that. So with my design, if I look at my design right now, if I put a preserved geometry at the top, I'll be able to see that because it will be able to go up right up to there. But if I had a flat plate that was obstacle, it's kind of stopping it, and it won't be able to come around and grow around that. We think about nature, how it works. This is really how we add this criteria into here. Okay. So yeah, I'm not going to do every single preserve and obstacle. I already have one set up for this, but it's kind of the same way I just did that with those two adding in there. I'm going to switch over to my next model that has the preserves and obstacles already built into it. And it's going to look like this, where our preserves have the top plate preserves are center of the holes there, and then our obstacles are going to look like that, because we need some obstacles that does not grow into the areas where we're bolting and connecting, and also that top plate where it's moving and rotating and rotating around there. Okay, so let me pop over to my next one here, and I've got my preserves there, and I've got my obstacles there, so it's going to look something similar like that after I'm done with it. Okay, with this, we've got get to my preserves done here. There we go. We've got the preserves and obstacles done. And what we got to do now is we got to add some loads and constraints. So if we're thinking about left to right here, we're right now in our preserves, our design space. We're going to go now to our design conditions. We're going to add our constraints and our loads into this. So by adding a constraint and load in there, we can come in and into our load case, into our study, and add our loads and constraints. And that's what those buttons here do with the structural constraints and structural loads. So let me pop over back to this here. And we're thinking about this caster wheel. We've got some different loads on this. So of course we've got our weight and everything, and the pushing down on that wheel. We've got, when we move the wheel forward and backward, we've got the loads horizontally that way. And we also got the floor pushing back up on that. So we've got the load there too. So we can actually add our constraints and our loads in pounds, or we can add it in newtons, depending on what you type in. You can actually have different units inside of there. And what we can do is we can add different load cases as well inside of there. So not only one load case. So what I would do is I would recommend having our multiple load cases where, okay, we have a load case up, we have a load case at like a 30-degree angle, and a load case at and like a negative 30-degree angle inside of here. Okay, so what I'm going to do is I'm going to show how to add a load on there, and also a constraint on the top there. All right, so I'm going to pop back into my Fusion just to show how easy and how this works. So I'm going to turn off my obstacle geometry right now, and I'm going to add, right now you can see there's a load on here that's actually this is gravity load. It automatically comes in. Of course, everything's going to be, gravity is going to apply to everything, so I'll keep that on. But if you wanted to actually make this to be used on Mars or some other location, or on whatever, you can actually change those magnitudes and everything in here too, and change those units. All right, so when I'm going to come in, I'm going to say I'm going to add a constraint in here. And we've got our different constraints: fixed pin, frictionless, or remote. I'm just going to add a fixed pin constraint on this, and I'm just going to select that target inside there and hit OK. Now that's fixed in place on that. And we can add other types of constraints if we wanted to, depending on your design. You can add those in. You can have multiple in there. So there's our load case. And with our load case, this is going to be, like I said, we have multiple load cases. We have the load case up, 30-degree, and negative 30-degree. Now, with this, I'm just going to add the load case up and then switch over to my next one with all the load cases. But I can show you how these work here. So with this load case, I'm going to pop in that, and let me pop in my information here. Make sure we got that. Okay. So I'm going to pop into loads, and I'm going to say, okay, this is going to be a force, but we've got other loads in here. We got pressure, moment, bearing loads, remote force, and remote moment loads in there. So I'm going to hit the force, and I'm going to select my target, and it's going to be inside of that in here. And you can see that it points directly up. So that's going to be our structural load going up at that point. Of course, we've got the rotation icons here that we can use to rotate our loads around. That would be how you would add the -30 and 30 by using the degree angles here. That's how you would add those different loads in there for one. You know, it rolls along. You can add the loads at different angles inside of there. So I'm going to hit that, and yeah, we'll say, okay, this is a magnitude of 200 pounds force. And I can add multiple loads to both of these as well. So let me undo that, and I can show you. So I can add both loads to that. So I can say the inside of that and inside of that to both of those, and then say, yep, 200. Okay. So if we look at that now, we've got our force there on that. Now for the load cases, I can right click and I can clone that one, or I can say new load case and just redo the load. If I clone it, it will actually clone that. I can rename these by slow clicking on these and say that's load case up. Maybe this is load case 30 degrees. And with this one here, I can activate that and say, all right, now this load is going to be, not this force, and we can say this is going to be, and I can even take a look and see, yeah, -30 degree angle. And I can then do that same thing for the 30 degree angle. Okay. All right, so let's pop back over. I did show the cloning there, so I can clone not only the load cases, but I can clone also studies and also generative models as well. So you can do multiple cloning inside of generative design, so that you can try different things as you go. Like I said, it's rinse and repeat, kind of trying things, going back. If I have a study, maybe I'll make a study out of certain load cases, but then have different manufacturing methods for multiple studies, and the same load cases on each one. Or maybe for the first study, I'll have an objective of minimizing the mass. Maybe the second study, I'll have all the same information, but that objective will be for maximizing the strength, the stiffness on it. And I can actually generate outcomes depending on what study I want. All right, so let me go back to my Fusion. So I should have now in this next one, I will have all of my load cases here. I've got my load case up, my load case at 30 degrees, and my load case at -30 degrees. So if I turn off my obstacle geometry, you should be able to see now, here's my load case up, 30, and -30 there. So what we got to do next is go to the next one, and we're going to go to objectives and manufacturing methods. And with this, the more outcomes that we're going to get, so the more manufacturing methods that we add in there, objectives that we add in there, the more materials we add in there, or manufacturing processes, it's going to come out with more outcomes, and it's going to be longer computation time. With this, if we don't want to sit there and wait for a really long time, maybe we make a study of just specifics of what we want to find out for. There is a limit of 24 hours of computation time and 150 outcomes per study. The study will stop if it hits any of those limits. And there is an outcome that generates per combination of material and manufacturing methods. So if I have multiple materials and multiple manufacturing methods in a study, it's going to multiply and make each one for each material and each manufacturing method combined in each one of those. So if I have 5 materials and 5 manufacturing methods, I'm going to have 25 different outcomes. Okay. Yeah, splitting into multiple studies. And yeah, specify your materials per manufacturer process. Makes things simpler, makes things quicker. Um, and yeah, making sure your outcomes have a purpose to these. So with the manufacturing methods, with the two and 2.5 time milling, axis milling, there is the manufacturing methods. Those manufacturing, all the preserved features must be normal to the same plane because we're thinking about 2-axis. It cannot rotate the milling head around and use like a 3 to 5 axis. So we're thinking about one the same plane. So all of those preserves must be on the same plane if we were going to be using those. For this one, then too, we're going to set our objectives and limits, and with our factor of safety, the safety factor there. When we think about a higher factor of safety, we're thinking about more resilience against unforeseen circumstances. Now, if I just put a safety factor of 1 in there, it's going to probably, that component, when we go to produce it or create it, it's going to probably fail when there's any more than the design load on it. So if we say that the load is going to be 200 pounds, 200 pounds force, and we have a factor of safety of 1 in there. So as soon as that load exceeds 200 pounds of force, it's going to fail with a factor of safety of 1. So usually a factor of safety of 2.5 to 4 is commonly applied, but I think for this example, we're going to try like a 1.25 and see what it comes up with. A little bit higher than the 200 pounds. We know that the design is only going to hold 200 pounds or less. It might be only 25 pounds or 50 pounds. So we'll use that, just bump it up a little bit. And we're going to set our manufacturing methods as well. All right, so with that, let's take a look and see what we've got here in our Fusion. And we've got our objectives. So we can say, okay, let's minimize the mass on this or maximize the stiffness. And we can set our safety factor depending on what we want here as well. We can add modal frequencies, displacements, if there's any buckling inside there. Some new things that they've added in here recently inside that. So really the things that we need to input at the minimum is either the maximized mass, stiffness, and the safety factor that we want in here. And we can also add the manufacturing methods that we want to add in here too, whether we want it unrestricted. Unrestricted means doesn't care about the manufacturing method. It's going to just go ahead and create the design however it wants, unrestricted. It does not take into account any of the method of manufacturing. We can also add additive in here, milling, and we can have 3-axis or 5-axis in there. We can also do die casting as well inside there. And what I would probably do, this is just a demo. I can add. I've added a bunch in here, but I probably make multiple studies in here and have probably additive as the first study and milling as the second study and die casting as the third study in there. And then we can add our materials. So let's get into the materials here. So we've got materials built into the Fusion as libraries, and we can select materials directly from there. We can add up to 7 materials in total, and it actually has all the information inside of those materials in Fusion, depending on the actual what it's made of and the specifications of it. And since we should be specific on when we go to create studies and generate these, you should probably remove the unneeded materials from the manufacturing methods inside there. So if you're not going to be, you don't care about anything that's like nylons or rubbers or anything like that, you can remove those from the study. That way it doesn't go and try to produce those outcomes from that. Okay, so let's go into this here. And I've got my materials. Take a look at that. And let's add those materials inside of here. So I've got additive materials, I've got the nonlinear, I've got material library in here. I can say, okay, let's make this out of like aluminum. Just drag and drop it up there. If I want to make it out of stainless steel, yep, go ahead and drag it up in there. And then those materials are what can be generated out and created without the outcomes depending on the material and also the manufacturing method that we had set up inside. Then at that point, what we can do after we've set up all this information here in the very beginning up to that panel, we can then do a pre-check on this. So a pre-check means that it has all the information needed inside of that. And I've got a slide on this as well, but we also have this previewer too, and the previewer will allow you to preview kind of what generative design is going to do. This is a free option to be able to preview this. It's not going to be as refined as what we get from actually generating the outcome and seeing the finished outcomes there. But it's going to be doing this. It's a local simulation. It's generating all local here. It's going to take those preserves and that obstacle geometry and show a preview of what it kind of thinks it's going to do in the very beginning. It's really, really rough. As that's working, let's talk about that. So it's cheap, fast, and easy. Yeah, it's free to do. Once you need your finished designs, that's when it's going to take your tokens. Yeah, and with this preview, I like using it too because it will let me know what we need to change and set up, what preserves we need, if there's any obstacles that we need to place more obstacles in there so that it doesn't build and create the design inside of that. And it's just, so the previewer is going to just select the first material, so and that unrestricted manufacturing method, just to give you a quick view of that. So let me go back here and let's take a look and see how our previewer is doing. It's taking a little bit longer than I thought, but you can see as it starts to create it, it does that there. And I can pause that and continue along anytime the way here. So I'm going to pause that. All right. Stop that there. All right. As I go through, there is some other options inside of generative that we can use. So let's take a look there. Symmetry planes and starting shapes. So with the symmetry planes, what this is totally optional. For something like this bracket that we're going to be using, it is symmetrical about both sides of that plane, of that origin plane. So we can set that origin plane as a symmetry plane, saying, okay, everything that's designed and created on this side of that plane, make it symmetrical on the other side of the plane. So the design after it's done looks symmetrical. And we can define that with a symmetry plane. And we can also use a starting shape. So this is more of the more adding in a little bit of topology optimization, where I can say, okay, I have this legacy design. Let's use it as a starting shape and kind of say, all right, let's start that and make that like an aesthetic for our designs, the outcomes that it comes out with, and kind of make it similar to what we already had started with, and build those outcomes kind of, starting with that shape, but make it kind of similar to that. So it kind of it influences a hair on how it's actually going to outcome and how it's going to look at the end. So with that, I can set up a symmetry plane here, and I don't think I have any set up. Oh, I do have one set up. So let me actually remove that one, and I'll show you how that works. So with symmetry plane, we just click on that and we say, okay, what plane is in the center of the symmetrical location, like a mirror plane there. So I'll just say, okay, we've got a plane that's directly in the middle of this design. Let's just use the XZ plane. And the XZ plane, so that way it's symmetrical on this design, the design on this side compared to that side over there. And okay, easy enough. That's all you have to do for that. Then we can also, like I said, with the starting shape, now that symmetry plane and starting shape are optional. So the starting shape here, we can use, I can turn back on the model components, turn back on that. frame inside there. Let's turn that back on and say, okay, starting shape, and let's pick that. And we can use the topology optimization. There's some options down here when we want to add or remove the material from that starting shape, or just remove it fully. Topology optimization there, and kind of influence the end design. So that's how we could do that. And those are completely optional. For this demo, I'm just showing this how you do it, but I don't have it actually on the outcomes. So let's take a look and go ahead here forward. So we've got some warnings also. I did show off of the inspector there, and you will have some warnings if it doesn't have certain preserves, or if it doesn't have any load set up to it or constraints set up to it. It will give you warnings on this. So you should not ignore them. Sometimes you can ignore them depending on if it's maybe some milling heads, or if they're too large or whatever, depending on what, if you actually are going to manufacture this or not, and if you don't have the right criteria in. But the ones in red, you will not be able to generate until you fix the warnings in the red. And that was located directly here in the pre-check. Okay, yeah, just some information on synthesis here. There is study settings on what kind of resolution we want when we go to output these. Whether we want to coarse or fine detail, keeping it in the middle kind of makes the outcomes go a little bit quicker, and I should say it's faster solving. Once we do it, the fine synthesis is going to take a little bit longer for it to have the outcomes, because it's trying to really refine the design at the end. Okay, so that's where we have the settings in there, and I would just leave it as default if you're just trying this out. But then eventually, if you get more advanced inside of generative design, you can start playing around with this resolution and everything. Or if you need something fully optimized, you can then set the resolution to fine. So after we have everything set up, so all of this is set up. Let me come down here to my outcomes here. Let me get back to my part here. After we have everything set up, we have a green check. We check the previewer. Hey, it looks good. And at that point, then we can hit the generate button. The generate button will allow us to then take this study that we have selected and then generate that. It sends it off to the Autodesk cloud. It generates all on the back end. It does not use your processing power on your machine. It will allow you to send it off. You can actually close the design. You'll get information back saying, hey, it's done. You'll get a notification here, outcomes are done. And if you keep the design open, what it'll do is it'll actually start to open up in something called the Explore window. And the Explorer window will give you all of the outcomes coming back that it's actually generated, depending on the manufacturing methods and also the materials. So we can see that we have some recommended outcomes here at the top. These are the ones that have converged, they're called, and those are the ones that are completely done, that's actually found the solution for them. The ones that are there might be some that are called completed, not in this example, but if they are ever say completed, means it actually stopped before it could actually hit the intent, the criteria that you had set up. So converge means it's, hey, we got it at a certain iteration, we're good to go. And it gives us recommended ones here at the top here. And I can look at these as a thumbnail view, and I can filter these out by volume, mass, and everything like that, objectives. I can see properties of each one as well. I can see a scatter plot view, and you can see that, okay, we've got different colors for our different materials. We have the ones with thumbs up, meaning the ones that are good. And we also have, and we can set up in our volume and mass or whatever for this, the vertical values, or the horizontal values. We can set these as well inside of there. We also have a table view, so we can sort by different columns also there. Now, when I have a converged study that I like, that's a recommended outcome, maybe I want to take a look at that. Well, what I'm going to do is I'm just going to come in here and I'm going to double click on that, and it will open up that design. Okay, so let's go back into here. We can see the results, and we've got our display panel I talked about. We got the filtering, and let's take a look at more of this. So we've got that result. Just open it up. You can see the information about it on the right-hand side. We can see it as a model view. We got our transparent view. We also have our stress view in here, so we can see the different stresses on this. Because it is kind of doing a simulation also on the fly as well as it's being generated. There's design previews of what's going to look like when you export designs. You can actually see the preserved geometry and also the obstacle geometry. So if we take a look at this, you click on the model view and then rotate this around here, you can see that it has not grown into anything that we set as obstacles. So it's taken the preserved geometry and grown from that preserved geometry down to the other geometry we have, but it has not grown and created any structure inside of the obstacles that we have. Okay, and I can actually take a look at another one here. Let's take a look at this one here. And let's look at that. So this one's a little bit more, probably maximize the stiffness and the strength of this one. You see it's kind of grown around the obstacle there. And also here at the top where we have another bolting connection, it's grown around that. Go back to that one. Okay, and with this we can actually compare other ones as well. So we can compare that to that one that's a little stronger. We can take a look at these both together. And let's say, hey, let's use that one on the left. We'll keep that one open. We can then add labels, tags to it, but then we can actually export this as designs. We can export the mesh out to that. With those, then we can use those in our assemblies. So let's get back into here. Yeah, so we got that creating design from the outcome. That's going to be your solid body that's going to export out. And then we can then create the mesh from that. And yeah, it's not going to be as accurate because it's going to be your tessellation and everything in there. And then after you export that out, you can use it in an assembly or whatever, but then you can also take it to like a simulation because there is the simulation workspace directly within Fusion. You can switch it over to simulation. You can also switch that over to your manufacturing workspace. So then you can actually manufacture that and set up your tool paths and your manufacturing study there for you to be able to create that, your process, and then simulate that as well. There is also an ANSYS mechanical export on this too. You can export that out for more stress simulation. And then we also have the troubleshooting on this. So just to cover this really quickly, yeah, if you have a higher factor of safety, not an issue of itself. It just means that it's trying to really bolster weak areas. So maybe something needs to be changed in, your loads, your constraints. Maybe it won't be able to handle the actual stresses and loads that you're putting on. Yeah. There is some information about maybe you had some geometry that's separated. So sometimes you'll get back some outcomes that have like it's cut off from each other, and yeah, maybe the loads are too low for a certain material, or your preserves are maybe they are in line, but maybe they, depending on where your obstacles are, maybe it's just should be moved a little bit, that it cannot connect each other. Yeah, it's really about, I'd say about this one, about disconnecting is the load on the material. So choose a different material or increase the load on there. We also have blocky outcomes. Yeah, material is too weak for the given load. So that means that I tried putting a load of maybe 500 pounds on this, and it was made out of plastic, and it could not could not create that. So it's going to give me a really blocky outcome because it's going to try to put a lot of material in there to strengthen that up and be able to get to that limit. And if we don't have any, if we have small, only like one or two converged solutions, or we don't have any converged solutions, then yeah, you would want to hover over each one that's says completed, and it will actually give you information about what it actually did and why it couldn't converge. Yep. Yeah, and I would probably kind of separate studies, or yeah, and also with these fewer no converged solutions, more than 10 loads per case will add complexity to it, so it might not be able to get to that limit and to that objective that you're wanting. Yeah, and also really thin reserves and obstacles. So with any type of simulation, since this is kind of a simulation product, anything that's really, really thin really does not work in simulation. So just got to double check that also. All right, so let me get back to my Fusion here to make sure there's nothing else. Yeah, I think we're all good in this. I think it's all complete. We also have, let me just show you one more thing here before I get into the end. We also have I have a example here of multiple studies. So if we look at, we've got study one here that has certain objectives. Maybe it's different loads in here. I have another study here that I actually cloned, and you can actually change the loads if you wanted to. Like, go back down here to my load and say, okay, instead of that force, let me activate that. So I can add more force to that one if I wanted to. So instead of 200, maybe it's going to be 300. And then I can actually output this with generative depending on the study that I want then at that point. Pick and choose which one's active to generate. And so I can have this all in one file, multiple studies, multiple methods, multiple load cases, all in one here. So I don't have to create multiple files. I just do it all in one design. Okay. So with that, if you need more information, yeah, we're here to help. You can reach out and find out more. We can also help out with anything specific. There is also the self-paced learning, the help and learning documentation directly from Fusion, and that self-paced learning does have generative design in it. So if you need any help on there, you can go through there. There also is some links, yeah, on Autodesk about learning Fusion 360. If you don't know Fusion already, you can go there, and there's also the Fusion help, and of course Fusion on YouTube. I just checked it recently. I think it was like 1,700 different videos on Fusion on YouTube. But yeah, we're always here to help on specifics and talk to you about using generative design. So with that, thank you everyone. And let's take a look now and see if there's any questions. Okay. Karthik asks in part A of the question, in the caster frame example, the analysis being done is a simple static analysis. Will the runtime not blow up if a dynamic analysis mode superposition followed by a harmonic analysis done on every iteration? Runtime not blow up. Yeah, so with part A of that question, Karthik, I would say that if you're going to be adding multiple loads on something, I would say make multiple studies, have all the loads on there, but then only have it maybe for one manufacturing method and one material. That way it really cuts down on how many it's trying to solve on there. So maybe if you do have a lot of loads or constraints on there on that for analysis, you're going to only want to have it specific for that. That way it cuts down on that. Part B, when material is removed, the domain needs to be remeshed, contacts established, the system bring back the same input. So really, what generative design is doing, it's not actually removing material. I mean, on that starting shape, it kind of influences it, but what it's doing is it's not actually a topology optimization where it's removing material. It's actually growing and starting at the very beginning of what you set as the objectives and loads and constraints and everything in the very beginning. So it's starting at the very beginning. So it does not I should say, try to reconfigure itself as it goes. It starts at the very beginning and starts with that design and kind of optimizes it from the beginning and starts from there as it designs it. Does generative design use any AI or machine learning algorithm? If yes, where is artificial intelligence coming into play in the caster wheel example? Where are settings for those machine learning models? So it's not machine learning, it's AI with their algorithms that they have. Autodesk has proprietary stuff in the background. What it's doing is it's using their AI and it's learning from everybody that's doing this. It's actually learning about different things. I don't know if it's actually a machine learning algorithm, but I think it's something else. But they're actually doing that in the background that we can't really touch that or learn about that. Maybe something to reach out to Autodesk about if you're interested in that. There is no setting for that. So what we do is for generative design, we just set up these constraints and parameters and everything, and send that to their systems, and they do the calculations and everything on their end. Oh, another question here from you. What additional constraints are being applied in generative design to differentiate from topology? So, like I said in the very beginning, it's not necessarily taking a legacy design or a starting shape and removing the material. This is actually building that from the objectives you give it. So it's the opposite of that. So it's actually like you're starting with those bolted connections, and then it's actually creating, growing the design directly from those objectives. So that's what really differentiates it from topology. Topology is removal, and the generative design is actually adding and creating. Number 3, in dynamic loading environment, a part strong in one direction may not be strong in another direction. Often we end up running something like a spectrum analysis in different directions. Visual runs are computation very expensive on assembly, since generative design needs multiple runs. It looks at realistic assembly. Yeah. So with this, it depending on how much you're going to add to this for realistic assembly. A lot of times, what I found, if it's a lot of parts to this and everything like that, it does take a long time, and there is that limit of 24 hours, 150 computation or 150 outcomes. And like I said, was the trial and error method. So even if you do add some methods on or some loads and constraints on there that might run into that limitation, maybe you want to start limiting some of your manufacturing methods, your materials, running on specifics, and then make multiple studies of that in there. Hopefully I'm answering all your questions. And then question 4, 3-axis generative design does not look as symmetric as a human-made design. How do you correct that? So using the symmetry plane will allow you to make it symmetric on both ends, depending on where you put that symmetry plane at. You can also then take that design, and like I showed in that video of the motorcycle bracket there, you can then modify the design a hair here or there if you wanted to make it more symmetric. or visually if you wanted to make it look more symmetric. But that symmetry plane should handle that for making things symmetric about that plane. And if I didn't answer the questions in detail, we could also grab these questions, and if you had more follow up on that, you can also shoot us an email, and we can get more detail back to you. Or if there's something that we don't know, we can also run it through Autodesk.